Hello everyone, how you guys doing? Welcome to our MIDAS Expert webinar and thank you for joining us today. I'm Sun Q and I'll be the moderator for today's webinar. Today's case study webinar, PSC Segmental Box Girder Bridge Design, is presented by Angelo Tinga. He has 6 years of experience in design for local and international infrastructure projects and also is very knowledgeable in both structural and highway design with familiarity of various international standards. In today's presentation, he will introduce you the definition of PSC Box Girder and what to consider when designing, and an example using MIDAS Civil. During the webinar, if you have any questions about the content, just type it in the question box in the control panel. We'll collect them and have them answer after the session. You'll be able to get the answers via email. And if by any chance you miss some part of the webinar, please do not worry. We'll send out the link to the recorded version to your email and also the PowerPoint materials. Alright, thank you guys. This is it for the introduction and now we're gonna get started. Enjoy the webinar.
Hi everyone. Thank you for joining today's webinar. My name is Angelo Tinga and I will be talking about PSC Segmental Box Girder Bridge Design. This webinar will be an introduction to PSC Segmental Box Girder Bridges, with a short demonstration on how you could use MIDAS Civil for your projects. This presentation aims to first introduce PSC Box Girder Bridges and the corresponding segmental construction methods. Next, to be familiarized with the concepts and theories regarding the design of PSC Box Girder Bridges. And lastly, to learn the different features that MIDAS Civil can offer. Here is the outline of topics that we will be talking about in this webinar. First, we will be talking about PSC box girders. Next, we will then be talking about segmental box girder bridges. Afterwards, we will be talking about design considerations that we will need to consider. And lastly, we will have a short demonstration on how you can use MIDAS Civil. So to start the presentation, let's discuss about PSC box girders. Some of you may be asking, what are PSC box girders? Pre-stressed concrete or PSC box girders are concrete sections forming a box shape, which may be rectangular or trapezoidal, that are mainly supported by pre-stressed strands. This type of girders are widely used for footbridges, highway bridges, and railway bridges. PSC box girders offer significant reduction in self-weight for longer spans and have high torsional stiffness due to their closed shape. Here we have a sample single-cell box girder cross-section. The basic components of this box girder are, first, the top slab, which is normally defined as the entire width of the concrete deck, including the portions between the webs and the overhangs outside of the webs. The overhangs, which is also known as the cantilever wings, are the overhanging portions of the top slab. Webs are the vertical or inclined segments, and the bottom slab, which is the entire concrete horizontal segment at the bottom of the section. For multiple cell box girders, the only difference would be having more than two webs, which are classified as either interior or exterior webs. Now, we would be talking about the materials that make up our PSC box girder. First, we have concrete. So for PSC segmental bridges, usually, high-strength concrete is used due to large compressive stresses carried by the sections. In practice, a minimum of 35 MPa concrete strength at 28 days is required. Higher strengths of concrete, which result in a higher modulus of elasticity, also helps minimize long-term creep deflections. Next, post-tensioning anchorage system, which collectively refers to the technologies used in anchoring tendons, are a proprietary system. The basic parts of a post-tensioning anchorage system are the bearing plate,
the trumpet, the wedge plate, which is also known as the anchor head, grout caps, and grout ports. Moving on, ducts are also part of the PT system. Ducts are used to form a continuous void throughout the concrete for the placement of the post-tensioning steel. Ducts are either made up of corrugated metal or corrugated plastic. There are a lot of available high-strength pre-stressing strand configurations, but the most common one would be the 7-strand wire. These strands are commonly available in 0.5 and 0.6 inch diameters. These strands and the ducts can either be installed internally or externally. After post-tensioning tendons have been installed and stressed, they are now usually grouted. Cementitious grout is made up of a mixture of Portland cement, mineral additives, aggregates, and others. Grouting provides bonding and immediate corrosion protection as it is directly in contact with the post-tensioning steel. Lastly, ordinary reinforcing steel is also a part of PSC box girders. The reinforcing steel serves as the backbone of the section and contributes greatly to the shear capacity of the girder and the transverse strength of the slabs and webs. Reinforcing steel with yield capacity of around 420 MPa is usually used as a minimum for segmental bridges. So, why are box girders used? Box girders are considered as one of the most flexible forms of the bridge deck. Box girders allow economical range of spans from 30 meters to 300 meters, which can go even higher with suspended bridges. They are also able to accommodate decks that may be up to 30 meters wide. The shape and reduced number of required supporting piers is also aesthetically pleasing. If you look to the right of the slide, these two PSC box girder bridges are part of the world's longest bridges based on their max spans.
Taken from a section of the book titled Bridge Engineering Handbook Superstructure Design, we can see the different economical span ranges for different types of concrete bridges. It is worth noting that for spans above 50 meters, we are only left with using box girders.
Now, we'll be talking about segmental box girder bridges. By definition, segmental bridges are bridges that are built via combining sections, called segments. For segmental PSC bridges, single or multiple cell box girder sections are generally used. The box girder segments may either be cast in situ or precast off-site. For the post-tensioning system, they can either be bonded, unbonded, or a combination of both.
The technologies used for segmental PSC box girder bridges have actually developed over several decades. Here, I'd like to enumerate some important milestones that made the technology as it is today. In 1939, the conical wedge post-tensioning anchorage system was developed. With this development, the technology was used for precast, pre-stressed segmental construction in 1941 to 1949. In 1951, the modern long-span cast-in-place segmental bridge was developed. In 1954, the dry joint match casting innovation was applied for the first time, which was later followed by the application of epoxy-coated match cast joints in 1962.
Precast and cast-in-place segments have different pros and cons. For precast segments, there is a better consistency in segment quality as they are produced in a specialized plant or environment. Fabrication of the segments can also commence as soon as the start of early field construction activities, thus improving schedule. Though, they are highly dependent in logistics and transportation limitations. For cast-in-place segments, they can only commence once the substructure has been completed. Though, their appeal is that there are no transportation and logistic limitations, so they are preferred when working in restrictive sites or when requiring large or heavy segments. Next, I'd like to talk about some construction methodologies used for segmental bridges. The different construction methods are one of the defining traits of a segmental bridge, and these construction methods are of critical importance when considering the design. The construction approach greatly affects the layout, tendon placement, and loads considered. Some notable construction methods for segmental box girders are the balanced cantilever construction or free cantilever method, the span-by-span construction, and the incremental launching method. First, let's talk about the cantilever method. The cantilever method, which is one of the iconic construction methods, involves the formation of cantilever arms from a support pair. When two opposite free cantilever structures are formed and erected at the same step, it is termed as the balanced cantilever construction method. This method allows the construction of long span bridges with main spans from 50 meters up to 300 meters. Cast in situ or precast segments are both usable for this construction method, with different equipment required. For example, for cast in situ segments, form travelers are used. And for precast segments, we can either use the ground cranes, overhead launching gantry, segment lifter, or beam and winch. I've prepared a simple animation to help us further understand the cantilever method. For this case, we'll be using the balanced cantilever construction method as an example using cast in situ segments. The use of precast segments will somehow be similar with this example. So first, the start of the method involves having the substructure completed. So this involves our column piers and our bridge abutments. Next, formworks are then installed at the top of the piers in order to cast the pier segment. With the pier segment completed, it is then possible to set up the form traveler equipment. Having this set up means that the next segment of the bridge can then be casted. After a number of segments, a second form traveler can then be set up on the other side. From here on, segments are continuously casted in parallel. Eventually, the tie-in to span ends are then prepared. An option would be to prepare a segment constructed on false work that will meet the cantilever, or the form traveler can continue until the end of the bridge. Note that temporary supports must be considered in this option. The spans are then closed or stitched together. And then the bridge is completed. The cantilever method has its advantages and disadvantages. For advantages, we first have minimal requirement for false works. Next, simultaneous construction is possible for all piers. Next, the navigation or traffic under the bridge is not or minimally interrupted during construction. And lastly, longer peer-to-peer spans are possible. For the disadvantages, the segments experience high negative moments during construction. Next, there is a heavier overall structure due to stability requirements. And lastly, there is complex construction and maintenance involved. The next construction method we will be talking about is incremental launching, where the bridge is constructed in successive short segments. A casting yard is located behind the bridge abutment, which produces segments 15 to 30 meters in length. Starting with the steel launching nose, the segments are launched by either being pushed or pulled forward towards the direction of construction. At the right side of the slide, you will see an example bridge in Germany which utilized incremental launching. Incremental launching starts with the installation of the launching nose, which is normally 60 to 80% of the longest span length of the bridge, and casting of the first segment. The launching nose and first segment are connected via monolithic or stressed connection. Next, the launching nose and first segment are then moved forward, in this case using pulling jacks. Afterwards, the next segment is then constructed and connected to the first segment. The segments are then further launched forward. From this point onwards, the previous steps are repeated. Incremental launching also has its advantages and disadvantages. For the advantages, first is that this construction method is able to span inaccessible or environmentally protected obstacles. There is also minimal disturbance to surroundings, no false work requirements, and reduced area requirements for superstructure assembly. The method is also highly mechanized, which increases work safety. However, the method has its disadvantages as well. First, it will not qualify as the most cost-effective method of construction. Also, launching is carried out by specialist contractors, which may increase the cost of the bridge. Also, special bearings are required at the supports, and the sections will experience both sagging and hogging moments over the course of the launching. Lastly, let's talk about span-by-span construction. Span-by-span construction is now typically meant for erection of precast segments and then post-tensioning for the entire span. It is the most common, simplest, and often most cost-effective method for medium span length bridges. If you look to the right of the slide, the top picture is a photo showing segments being lifted by a launching gantry. And then, if you look at the photo below this is a photo of the long key bridge, which is one of the early applications of the precast span-by-span method in the US. The span-by-span construction method is usually carried out by first setting up a lifting gantry over the span under construction. The first segment, which is usually the rear segment, is delivered on site and is lifted. After lifting, it is then positioned on temporary bearings. Afterwards, the second pair segment is then lifted and is also positioned on the temporary bearings on the other side. Afterwards, all segments are then one by one lifted and hanged. The segments are then positioned. Epoxy is usually applied at the joints and temporary stressing is applied. Note that epoxy may not be applied at the joints in some cases. These types of joints are called dry joints and is now not commonly used due to durability concerns. The permanent post-tensioning strands are then installed and stressed to final values. Lastly, temporary works are removed and the span is completed. With this, the gantry is then moved forward in order to construct the next span. Now, here are the pros and cons of the span-by-span construction method. This construction method is known for its fast erection times, no false work requirement, and the process is mostly repetitive, resulting in higher efficiency and safety. However, the span-by-span construction method also requires special launching gantries. Traffic under the bridge is also interrupted from time to time when precast segments are lifted. Lastly, this method is only considered economical for spans less than 60 meters. Moving on, Let's now quickly discuss design considerations that have to be considered when working on segmental PSC box girder bridges. The first part of the design process is the conceptual design. This stage involves the determination of the span arrangement and overall configuration of the bridge. It should also factor in functional, economical, and aesthetic requirements of the project. Establishing the layout is of most importance when working on bridges. As the designer, you have to factor in that each bridge or site faces a different set of jurisdictional, technical, and site-specific criteria. Some common factors that are considered are the nature or function of the site topography, the required clearances, especially if there are any roadways or waterways under your bridge, the expected traffic volume, environmental constraints, the structural system that will be used, and all applicable codes and regulations. Also part of the conceptual design is the estimation of the preliminary sizes of the superstructure cross-sections. For spans up to 75 meters, constant depth sections are usually utilized. For anything longer, sections with varying depth is more economical and efficient. The superstructure width is dictated by the owner and traffic requirements. Here are some common estimates used when determining preliminary constant depth sizes. The equations at the right are estimates from AASHTO LRFD. Additionally, here are the common estimates for variable depth bridges. Note that these are all estimates and the final sizing of your sections will depend on your design and other factors. Now, I'd just like to run down different loadings that you have to consider when designing the bridge. First would be the permanent loads, next the live loads, the temperature loads, the time-dependent loads such as creep and shrinkage, which are very important for PSC box girder bridges as these directly affect the stress in the post-tensioning steel. And we also have the post-tensioning loads, which include the axial loads, secondary moments, losses, the effects of curvature, and others. It is also of most importance to consider construction loads, such as the construction staging loads, the weight of equipment, and others. Wind loads are also present, and there may be other loads that are applicable to your project. Next, the longitudinal design of the bridge is the verification of the superstructure cross-sections at the relevant limit states. The usual bridge modeling and analysis principles are still applicable, but post-tensioning effects, time-dependent characteristics, and construction staging and loads are more critical. All cross-sections along the bridge must satisfy all flexural requirements based on the relevant design codes. Normally, design codes follow these assumptions when calculating the flexural resistance of a section. First, the natural relationship between concrete stress and strain is considered satisfied by an equivalent stress block. Next, the tensile strength of concrete is ignored. And lastly, strain is directly proportional to the distance from the neutral axis, with some exceptions. Next, the cross-section shall also be sized and reinforced to resist shear and torsion. The general procedure is first to check if the effect from torsion is negligible. Next, to check possible crushing of the girder webs. Next, to check the flexural shear capacity. And lastly, to check web shear cracking. Another important analysis for box girder bridges is transverse analysis. The box section is exposed to a complex mix of forces, so a three-dimensional analysis is considered the most accurate representation of real-life effects. However, this is seldom done due to its complexity and tediousness. In practice, it is more common to consider the section as a two-dimensional plane frame of unit length. In creating the transverse 2D model, the following are considered. First, the width of the beams are set to a unit length. Next, the top slab, bottom slab, webs, and overhangs are modeled as beam elements. Next, nodes are located at intersection of elements, changes in thickness, changes in member orientation, and for convenience of output. Lastly, vertical supports are considered at the bottom of the webs. For live load analysis, truck wheel loads usually present complex distribution problems. When using the simplified two-dimensional frame approach, there are three ways of handling live load distributions and ensuring the proper distribution of wheel loads. First is by using influence charts that are based on the elastic theory of plates. Or, next, using code-prescribed equations and procedures. Lastly, we can also use a partial 3D finite element model, where partial means that 3D modeling only considers a partial length needed in properly determining load distributions. Lastly, it is also important that we consider the construction stage analysis. The construction method used for the bridge highly affects the final design and arrangement of the segmental bridge elements. Stability checks are also carried out to ensure that the structure and foundation are stable at all times. As an example, here are the expected construction loads as defined by the AASHTO LRFD code. Now, we'll have a short demonstration on how to use MIDAS Civil when working on segmental PSC Box Girder bridges. In designing our PSC segmental box girder bridges, there are a number of MIDAS Civil features that we can take advantage of. To name a few, for modeling, we have our various bridge wizards. There is also support for irregular sections and the ability to place tendons in 3D or in 2D. For the analysis side, the section properties of the boxes are auto-calculated. There is also a powerful construction stage analysis feature and completed state analysis. The transverse model can also be created automatically via a wizard. And the tendons are analyzed in 3D or 2D. Lastly, for the design, the bending, shear, and torsional strength of the sections can be automatically checked. There is also the ability to check the transverse rebars. And we can also check the stresses for all of these stages, including the different construction stages. And lastly, we can generate the results and print a formatted design report. So for our example, I will just quickly show the procedure when working on a balanced cantilever bridge. The overall procedure can be summarized as: first, we define the sections and materials. Next, we produce the structural model. After, we then check the different construction stages. Next, we add all other loads that are also relevant to the bridge. And lastly, we perform design and we export the results and the formatted report.
So at the start of any new project, it is always best to check the units being used. In this case, I'm using kilonewtons and meters. Then, to define the materials, we go to the Properties tab. and click on Material Properties. So let's say that I will be defining two types of concrete strengths. So for this case, I'll click on Add. For the first material, let's select concrete. The standard, let's say that we will be using the ASTM standard, and click on C6000. Clicking on Apply, we can see that this material has already been added. So let me just add the other material. So let's use C4000. I'd also have to add the material properties for the pre-stressing tendons. So I'll click on Steel. Standard, let's select ASTM as well. And for the database, let's use the A416-270 low relaxation steel. Click on OK, and the material has been added. Next, we can then start creating the structural model. So this is something that I'd really like to show you. If we go to the Structure tab and click on the FCM Bridge, this is actually the FCM Bridge Wizard, which will help us to automatically create a structural model. So using the wizard, we just have to understand what we have to input in the different text boxes. In this case, for the girder, I'll first select it as the C6000 material that we've already defined. For the pier, let's select the C4000 material. For the number of pairs, this case, I'll just like to set it as 2. For the pair section, we will have to define a pair section. So we can just click this button. So for this case, I'll just click on Add. And let's say that we will be using a solid rectangle as the pair section. So let's just name this as pair. And I'll set some arbitrary values. Now we can see that the section has been added. So clicking on Close, we can see that the wizard can read the new section. For the stage duration input, this is actually the total time to construct a segment, which constitutes a construction stage. So this involves the time it takes to install the formwork, the time it takes to place the reinforcing and sheets, and to cast and cure the concrete. For this case, I'll just set it as 12 days, and the method is cast in. Next, for this case, I am defining a straight bridge, so I don't need to input a value of the radius. Now I can input the values for the pair table, key segment, and pair sections. So the variables that you can see here are related to the guide diagram. Now I'll just be inputting some arbitrary values. Note that for the variable c, this defines the distance between different elements that support a pair. So if we want to define only one single element for the pair, we can just simply set this as 0. Moving forward, we can then define the values for the FSM zones. So looking at the guide diagram, the FSM zones are the ones that are located near the ends of the bridges or at the ends of the bridges. So the FSM zones are conventionally constructed with full shoring. So for this case, I'd like my left FSM zone to start with a 2-meter division. And then I can then input 4 divisions at 4.25 meters each. And to make the bridge symmetrical, I can just copy this to the right side. Next, moving on to the inputs for Zone 1 and Zone 2, which are the lengths of the segments located to the left and right of the first interior pair table, we can then set, let's say, an arbitrary value of 12 segments at 4.75 meters each. So let's just copy that to the zone 2 input. Leaving this as is, the wizard will then assume that the values for zone 1 and zone 2 for all of the pair tables will be the same. If we are working with non-uniform values, we can click on this checkbox and click on the Advanced button. And here, we can edit the zone 1 and zone 2 values for the different pairs. So let me just close this window and uncheck this because we want to define equal values for zone 1 and zone 2. Moving on, clicking on the pair table placing, we have to take note that in practice, not all the pair tables may be constructed simultaneously. So for this reason, we specify the relative times for constructing the pair tables. So for pair 2, for example, I'll set it to be constructed 60 days after pair 1. Clicking on Define, and click on OK. Next, clicking on Member Age, we can then define the initial age, which is the maturity of concrete at the start of a construction stage. So this member age is used to reflect the compressive strength, which also relates to the modulus of elasticity, and the creep and shrinkage values. For this case, I'll just be inputting some arbitrary values. And click on OK. So after we've input all the values that we want in this model tab and we're happy with it, we can then go to the section tab. So in the sections tab, we can then define the dimensions of our box section. So all of these variables are tied to this guide diagram. So for section type, we can select 1 cell or 2 cell. So let's just select 1 cell for this example. For the view option, we can view the bitmap, which is the guide diagram, or we can click on drawing to have a feel of what the sections now look like. So let's just click back on bitmap. Now, for the form traveler load, we can include the values of the point load and the eccentricity, as well as the option to include wet concrete load. So I'll be leaving that as is. If everything is okay under the section tab, we can then go to the tendon tab. So for the tendon tab, we'll first define the tendon properties. So right now, we don't have any properties defined. So let's just click on this button and click on Add. For tendon name, I'll set it as, let's just say top. Tendon type, we can select if it's internal pre-post tension or external. So in this case, we'll be using internal post tension. For the material, we've already defined our steel material previously. And next, the total tendon area. So for the total tendon area, we can just input it manually, or we can click this button. Next, we can just define our strand diameter. So I will be leaving it as 12.7. And for the number of strands, let's say 19. Click on OK, and the total tendon area is automatically calculated for you. For the duct diameter, I'll set it as 0.1. For relaxation coefficient, let's say we will be using CEB FIP 1990 model. So I will be leaving all the other values as is, but feel free to edit this with respect to the project requirements that you have. Now, clicking on Apply, the material is added. Now, for the bottom tendon, let's say that we will be using the same properties, same values, but we will be increasing the number of strands. So let's say 30 strands. Click on OK. And we will also have to edit the duct diameter value. So click on OK. The material is added. And we can then close this window. Next, you can then define your jacking stress. So this is something that the project will have specific requirements. So for this case, I'll be using 0.72 for top and bottom. Now, there are a lot of other inputs that we have to provide in this tendon tab. So these are very specific inputs that your project will have their own unique values. So in the interest of time, we will not be talking about them in detail in this presentation. But what I would recommend is to visit the MIDAS website and check on the page for the FCM Bridge, which will give you guidance in using the FCM Bridge Wizard. So if everything is okay in your model, section, and tendon tab, we can then save the wizard inputs. So click on Save As, and let's just call this, let's say, example 1, and save it. And if ever you will be needing it in another file, you can just click on Open and select that wizard file. Now, let's say that everything is okay with this bridge wizard. So click on OK. And the model is created automatically for you. So here we can see the final model produced by the software. So the model is already completed. So under the Works tab, we can see that the sections are defined, the boundaries are set, and static loads have already been assumed. So in this case, you can just manually edit it to suit the model to your needs. But as you can see here, the different construction stages have already been defined. So for CS1, 2, so moving through the stages, and then having the stage for the completed bridge. After the creation of the model, you may need to first verify the construction staging and construction loads are correct, and do any changes if necessary. Next, you will also need to add your time-dependent material properties for creep and shrinkage. Next, you would also need to add your moving load cases. You can do this through the Load tab and clicking on Moving Load. And lastly, you should consider your seismic loads if applicable. So here I've already prepared the finished model and I've already performed analysis. I've also added the load combinations for the concrete design as well. So we can see the results of the bridge under the Results tab, and then we can see the reactions, deformations, forces, stresses, and other results. So for example, if we'll be looking at the beam diagrams, we'll click on Forces, select Beam Diagrams, and then select the combination that we want to show, and click on Apply. After checking the results, we can then proceed on to the design. So under the PSC tab, first we will have to click on the parameters. So, and the design code. So let's say I will be using LRFD 17. Click on the parameters, and then these are the input parameters that you will have to define. So I will leave it as is. For the output parameters, I will click on Select All, meaning that I want the software to check all of these checking procedures, and then click on OK. Next, we will then have to click on the PSC design material to define the design materials. So, for example, clicking on C6000, we can also select the rebar. So in this case, let's select ASTM. Grade of the rebar, let's say grade 60 for both of them. And click on Modify. We can also do this for the C4000 concrete material. Next, we will then have to define our design and output positions. To do this, click on Design/Output Position and first click on Design Position. Defining the design position tells the software which elements it has to design. So we can select any of the elements. For this case, I would be selecting the entire superstructure and click on Apply. Next, we will be defining the output positions. So click on Output Position. Now, what this tells the software is that which elements it has to export the results in the formatted design report. So I will be selecting the entire superstructure and click on Apply. After everything else is okay, for example, the segment assignments and the concrete allowable stress load cases are defined, we will then just have to click on Perform Design. After the design has completed, we can then view the summary of the results under Result Tables. For example, I will be clicking on the Check Flexure Strength. And here we can find the final results for each of the assigned elements. We can then also export a formatted Excel report. To do this, click on the Excel report icon, and then we will have to select our language for the report and the unit. So I will be selecting the SI units, and then click on OK. As you can see here, the design report will look something like this. So it will also include all of the checks that you've selected when you've started the PSC design. So that concludes our short demonstration in using MIDAS Civil. There's a lot of stuff that we may not have discussed in detail, so I would recommend to anyone who wants to learn more about MIDAS Civil to check out the various videos uploaded on YouTube. And here I'd like to just share with you the various references that I've used for this presentation. And that concludes the presentation, and thank you all for listening.
Alright, I think that's it for our webinar today. Personally, it was a great opportunity to get to know about PSC Box Girder bridge design. I'm sure the audience also have learned a lot. If there's anyone who didn't have a chance to ask questions during the session, please feel free to email us at midasbridge@midasit.com. Also, like I said earlier, we'll send the recorded webinar and PPT file to your email. So thank you everyone who came today, and have a good evening. Bye-bye.